Hello, good morning to everyone. Welcome to the 11th session of the Probabilistic Machine Learning Reading Group. Today we have with us Victor Gallego. He did his PhD at ICEMAT and is now one of the founders of Comore BAI, startup based in Madrid. He's also teaching at IE University, and he'll be talking about energy-based models. Thank you, and the floor is yours, Victor.
Thank you, Pablo, Daniel. So I'm gonna share the screen and we can just continue with the talk. Okay. So let me just open the slide a little bit. I'm just gonna collapse this. Okay, the slides. Yeah, ready. Okay, let me just put in slideshow. Okay, so I hope you can see fully the slides now. Okay,
Yep, perfect.
so thank you. Good morning, everybody. Yeah, today we're going to continue with what is now chapter 24, okay, of the book by Kevin Murphy, which is focuses in energy-based models, okay, which is quite an interesting topic in my opinion. It's like a kind of a different approach from the different approaches we have seen, like variational autoencoders, normalizing flows. So we are gonna see what is very soon. All right. So, I mean, if you have seen the book, you have read the book chapter already. It's mostly focused on several training inference strategies for energy-based models, okay, which will be defined very soon. Okay, so it's gonna be like quite technical, but I found interesting that not only to just focus on the inference or training techniques, but I'm gonna try to show you some case studies, two big important recent papers about the large scale applications of EVMs in practice, which might be of interest. Okay, it's like there are two well-known papers with around 1,000 citations each, but it's good to know they're quite recent. So it's yes, a good, I think it's a good complement to the series of training and the definitions of energy-based models. All right. Of course, please ask me any questions at the end or just during the presentation. Don't worry about that. Okay. So let's begin. Okay, so until this moment, we have seen in our generative model tribe is several different models like BAAs, autoregressive models, normalizing floats. Okay, which they are really directed graphical models. Okay, they generate data like one step at a time using like conditional distributions, which are normalized at every step. Okay, so energy-based models is they are like an alternative modeling approach, okay, in which in principle we have more freedom when specifying the model. Okay, we are gonna see there are some problems that we need to solve. Okay, but in a priori we have a lot of freedom with energy-based models, as you're gonna see. Okay, and they are motivated because in some domains, I don't know, for example, in protein design, it's much easier to just specify constraints that our samples need to satisfy. Okay, so for example, protein may satisfy this property and this other property. Okay, so this idea of conjunction of probabilities or properties or constraints is can be like more defined in an easy way with a energy-based model. Okay, so that's a kind of the motivation. Okay, so instead of working with a normalized distribution as usual, we are going to be working with energy functions which are like the unnormalized counterparts. Okay, so this is really the actual definition. Okay, so energy-based model is nothing more than like this kind of distribution. Okay, in which we distinguish the energy function, okay, which can be unconstrained. So it's gonna be a function that, of course, it's parameterized, okay, and it takes inputs in the dimensional data space, okay. But this energy function can be any neural network, okay. So that, in principle, it gives us a lot of freedom, okay, because we don't need to impose invertibility like in normalizing flows or no autoregressive ordering. So in principle, it can be any function. Okay, so it's amenable to like a lot of domains like physics models or I don't know protein design, that stuff. Okay, but of course, while we have this freedom, okay, in the energy function, there is a trade-off, which you might be wondering, this is really the partition function. Okay, because at the end of the day, of course, we have a probability. Okay, so we need to normalize all of this. And of course, as you know, always the partition function is almost always untractable. Okay, so the thing is, these energy-based models, they are quite easy to design because we can specify energy functions freely. But the problem lies in how to deal with the normalization constant. Okay, and that's why, I mean, if you see the book by Murphy and what we are going to focus on the tags, there are like several strategies that I think they are interest for some other domains, but these strategies dealing how to deal with the partition function, normalization constant, or whatever you want to call it. Okay, so let's continue a little bit. Oh, can I just move? Okay, yeah. So this is also uh, some kind of this is related to the concept of product of experts, okay, which was introduced by Hinton, okay, while he introduces contrastive divergences, which we will talk about soon, okay. A product of experts is nothing more that like the formalization of what I was discussing just a few minutes ago, which is, okay, I have several properties of my data, like one probability distribution and two and another probability distributions. So I want to have a model that is really the conjunction of these two. So my any data has to satisfy these two properties. Okay. The thing is, if each expert is an energy-based model, we can just easily do the addition of energy functions. Okay, and the resulting is also an energy-based model. So this is nice because it gives us a way of composition different energy-based models just by adding up the energy functions. Okay, and then the normalization and that stuff. Okay, so this is just an example that appears in a paper that we will comment at the end. Okay, so suppose we have one property, which is the first energy function, which is these four potentials. Then we have another energy function, which is like this big plateau to the right. So the product of experts would be just the intersection, these two modes to the left, okay? And this is interesting because this is in contrast with mixture of experts, which are really different, okay? Because with a mixture of experts, we are just really first sampling the expert ID and then sampling for the expert. So this is really like averaging the densities, okay? This is really the union of the two probabilities rather than the intersection, which is what we are doing with a product of experts, okay? So it's like alternative approaches, all right? And that is why, well, at least in some kind of intuitive way, mixture of experts are more related with directed models, while product of experts are more natural in energy-based models. Just the way of this compositionality holds, okay? But this is really like some kind of nice property, okay, that some people in some domains make use of, okay? So now thing is we need to get our hands dirty, okay, because so far the definition, as you see, is quite easy because it's just some kind of energy function, okay, but we have the problem with the partition function, okay, because really because of this big constant, okay, we are, as you know, we cannot even evaluate the density or the likelihood, okay, but we cannot do at the moment drawing samples from energy-based models. So we are very, very broke, okay? So that's why the chapter 24 by Murphy mostly deals with like a lot of different strategies to fit these kind of energy-based models, okay? Which is what I want to show you, like different alternatives, okay? Some of them are quite intuitive, some of them are more advanced, okay? But we are gonna see a glimpse of all of them so you get like a flavor of what people are doing in research, okay? So first, we're gonna focus on like the usual, the most simple approach, which is maximum likelihood. Okay, so it's as usual, we want to maximize, okay, as an optimization problem, the expected log likelihood of the probability defined by an energy-based model, okay, which is this expectation, okay, and it's good to know that this is really equivalent to minimizing the QL divergence between the data and the model distribution, okay, but for the moment we we can just focus on the log likelihood part, okay. So the thing is, if we apply the definition, okay, we have the energy function and the normalization constant, and we cannot compute the second part, okay. But this isn't really a problem, okay, we're gonna see how this can be dealt, okay, because usually I said before that the energy function is unrestricted, okay, but as you might be wondering, we typically impose that it's a differentiable function, okay, so it's compatible with, the usual stuff we use nowadays like PyTorch, JAX, everything, okay. So really, to use maximum likelihood estimation, okay, we just take the gradients and optimize. And the thing is, we have now these two terms, okay, just by applying the gradients, okay. So the first term is quite easy because if the energy function is a neural network, we can just use automatic differentiation like PyTorch. So this is straightforward, as you know, okay. But now we need to also differentiate the partition function, which a priori is hard because we cannot even compute that, okay? But the thing is, okay, this is the first result of the book chapter in the Murphy's book, which is, don't worry, because we can compute really this gradient. This is really an expectation, okay. And I mean the proof is, I mean, it's quite straightforward because we just need to apply the definition of the derivative of the log and put the gradients inside the integral, okay. And then we recognize that this is really the definition of the same energy based model density, which is here, okay. And this is really just the definition of an expectation, okay. So this is nice because, as you can see, we have just by applying the calculus, if you want to say that, we have got rid of the partition function, okay, and we have expressed just as an expectation, okay. So we have also a same gradient of the energy function, which is easy to compute, but notice the difference because the difference now is that we are not using data from the data distribution, we are using data from sample from the energy based model. That's the difference from the other term, okay? And this is where we need to put some work now. So this would be really the gradient that we will use to use maximum likelihood, okay? Which is we have the first gradient of the energy function, okay? And then the other term that we have just simplified with the theorem, okay? Which is the model term, okay? So there is like an intuition in terms of energy, if you wanna see it like that way, which is the data energies we keep pushing down, okay, but the model sample energies we push them up. So it's like we are doing a contrasting because we wanna make sure our model fits well the data, but contrast with the model generated data. So to learn the difference, okay. So it's like this is why it's related to contrastive divergences and that stuff, okay. So really, until this moment, this is quite nice, okay? Because now we have a gradient to estimate the parameters of our energy-based function, okay? But and we have the data from some data sets. Suppose we want to fit images, so we can have a data set of images. What we need now is a recipe to sample from the energy-based model, okay? Which is what we want to work now, okay? So how can we do this? Okay, well, notice we are gonna do Markov chain Monte Carlo really to obtain a sample. Okay, so we need to sample from the energy-based model. Okay, and the thing is, again, since we can assume differentiability, okay, we can just take the gradient of the log PDF, but notice we take the gradient now with respect data x. Okay, so if we take the gradients, this is like very similar to before, okay, because the first part can be easily differentiated again, okay, and now we get rid of the normalization constant because it's constant with respect to data, okay, so we get a really nice expression, okay, without partition function, okay. So it's natural now to relating with the other topics, in this case to Langevin Markov chain Monte Carlo, okay, which is like, remember, it's like stochastic gradient descent, but using noise, okay. But the only difference, which is important, is that we are doing Markov chain Monte Carlo in data space, not in parameter space, okay, because remember that we are still doing maximum likelihood estimation, okay, but we need to use MCMC not for the parameters, rather to get data samples from the model, okay. But this is really the, I mean, I prefer that it's, for me it's intuitive, like, okay, we get an initial sample from the model, or well, an initial random sample, okay? Because at origin we cannot sample from the model. It's the problem we try to solve. And then we refine this random sample following the gradient of the energy of the model. So after several steps, okay, these there are properties, as you know, that if we reduce the step size and we take the iterations to infinitive, this population of samples converts to the actual distribution of samples from the model. But keep into account that this is for a given parameter theta. Okay, so the thing is, as you might be wondering now, this is really like a very slow process because for just one parameter update, we need to run a Markov chain Monte Carlo chain for a lot of steps. Then update the parameter, okay? And then with a new parameter, we should run another chain again. So you can imagine this is very painstakingly slow, okay? Because if MCNC was slow, running this for every parameter update is gonna be like a lot of slow. So that is the problem with this kind of approaches, okay? We have a, as you can see, we have a procedure to sample from the energy-based model, okay, using Langevin Markov Monte Carlo, but this is slow, okay? So now the methods that people have done in the literature is just ways of making this faster, making this sampling faster, okay? So we can update the energy function more frequently. I do not say so, okay? One of the most like this is I mean this is quite intuitive and it's like quite the obvious idea, okay? So since we need to run a chain at every parameter step is quite extensive, okay? Instead of just resetting the chain after each parameter update, I'm gonna start my second chain from the last point of the previous Markov chain Monte Carlo chain. Okay, so this is really that phrase from the last part. Okay, it's like in my Markov chain Monte Carlo chains, they have memory. So instead of resetting from scratch, when updating the parameter of the energy-based model, okay, I start from the previous iterate, not from a random sample. Okay, this is why this method, which is like the most used in practice for large-scale applications of EVMs. This is like what people use, which is just persistent, okay? Because as you can see, here are the steps, okay? So first of all, we compute the gradients with respect to our data points over a mini batch of data samples, okay? But now we need to compute the other gradient, which is respect the data generated by the model, okay? But as you can see, this is just running a chain of, let's say, I don't know, 10, 20 steps of the Langevin dynamics, okay? But the thing is, to avoid the very long runs, we don't restart the chain. We just keep flowing with the chain, okay? Which is, I mean, quite intuitive to do if you want to save time, okay? And of course, finally, we update the parameters, which as you can see, we have the two gradients. One is the gradient for the data part, and the other the gradient for the model generated part. And we just added them together, okay, to the model. Okay, so there are several variants, okay, to this approach, but this is really the approach that this is used in practice. In for example, in this paper, that this is really people at OpenAI at that time. Okay, they just use the approach. Okay, the thing is, you can really complement this with tricks. One of the most common is really the reply buffer trick, which I mean, this is gonna sound familiar to you for reinforcement learning. It's the same idea of in reinforcement learning, okay, to avoid staleness when updating the deep Q function in deep Q learning. Okay, you keep a buffer of previous experience, all right, and just you can just sample them at each time, okay, to improve the exploration of your chains. Okay, so this is really like an engineering trick. It's just something to avoid the model collapse and to improve the exploration. Okay. So also notice that these approaches, we are really truncating the Markov chain Monte Carlo. So the gradients we incur in some bias that we assume. There are some papers that explore the corrections to this bias, but they are quite niche. Okay, so this is really the state of the art in these elements. Okay, so this is really called like persistent this method, which is alternating gradients from the model from the data samples with gradients from model samples with Langevin. This is really called persistent contrastive divergence because it's really related to contrastive divergence, which is like one of the most important works of from Hinton, okay, from before the deep learning era, okay. So really, contrastive divergence is nothing more than just having a Markov chain Monte Carlo chain, but just run for one step instead of until convergence. Okay, so you can see that this chain updates minimize on the contrastive divergence metric here. Okay, so this is fast. This is a way of making it faster, obviously, because we are just running from one step. Okay, and this is like, I mean, this is nowadays this is not really used, but this is historically important because it was the way people train this kind of generative models, which might be familiar to you, like restricted Boltzmann machines. Okay, this was like I would say like a historically important model family because it's, as you can see, it's an energy based model. Okay, with this structure, I think this structure was imposed to make the gradients easy to compute. Okay, because in those years people don't have PyTorch or TensorFlow to compute gradients. So I think this is because of the structure. So then the gradients, when you compute the gradients, they are easy, and you can see that we have the same structure because the gradient here is really follow the like minimize the energy for the data point, but on the contrast improve the energy of the hallucinated point, which is the model generated point. So it's really a contrastive term. Okay, but the thing is, nobody uses contrastive divergences today because really what people saw in practice, especially from the previous paper, that persistent CD, like it's much better. Okay, you don't need to impose this structure because now with automatic differentiation, we can use an inner network, as you know, for the energy function. Okay, and it's much better to just keep the previous algorithm, which is the one used in the large scale studies of energy based models. All right. So this is really what we saw with maximum likelihood training. Okay, so it's we using regarded in the end we need to use Markov chain Monte Carlo to get samples from the model and then combine the gradients of the two. Okay, now we can see. I think it's quite interesting to see an alternative, which is score matching. Okay, which is I think in the Pablo slides for biasional inference they mentioned it briefly. Okay, but it's also quite an approach what was used in the community. Okay, so the idea is that instead of fitting the PDF or the log PDF, we are gonna fit the first derivatives. Okay, so we are gonna focus on fitting the derivative object. Okay, why? Because if they are the same, the original functions are gonna be also the same because the only constant possible is the normalization one. Okay, so that's why we can focus on just fitting the derivatives instead of the original functions. Okay, so we can take this object, which is sometimes called Stein score function. Okay, which is the gradient of the log PDF, but with respect the data. Okay, with respect x. So from before we know this is really the gradient of the energy function. We don't have the normalizing function on here, so we are good to go. Okay. And the thing is, with score matching, okay, which is an alternative to maximum likelihood, this is really minimizing this divergence. Okay, this was introduced by Hibaringen from Finland, like in 2005. Okay, and as you can see, I think this is like minimizing the like the mean square error, but we are talking, of course, about distributions. But you can see this is like the mean square error, okay, between the gradients of the log PDFs. Okay, so it's an alternative to maximum likelihood or KL divergence. It's a different approach. Okay, with its benefits, but its trade-offs, as we will see. Okay, the problem here, okay, we of course we don't have now the normalizing constant, okay, because this gradient doesn't depend the previous line, but we have now oh sorry, was I wanted to just showcase this. Okay, so this is good for now. Okay, but notice we need to work with this, which is of course this is unknown because we need to take the gradient with respect the data distribution. which is unknown a priori because we only have data samples. Okay, so we don't know how to work with this. Okay, but the other part is easy because it's just the previous line. Okay, so one of the main contributions of this paper, okay, we need to do some calculations that he saw that it's really, I mean, if you use integration by parts in the Fisher divergence expression, okay, it can be nicely rewritten this way. Okay, and notice now that we only need to sample from, we get a few samples from our train distribution, and then we just need to evaluate the score function, which is the gradient of the log PDF. Okay, so this is okay to do. Okay, but now is the, okay, this is also known because this is just the Jacobian of the score function. Okay, but I mean, this we can compute that because we know the parameters. Okay, but as you may be wondering, this is horrible to compute because this is quite costly. Okay, computing a Jacobian is a full Jacobian. Okay, because we need almost the trace. It's quite computationally complex. Okay, so this is really why this was really a thing that this was done in 2005, but this doesn't scale to high dimensional spaces. Okay, because well, it's a known result from automatic differentiation that computing the trace of a Jacobian is quadratic in the number of dimensions of the data. So it's this really doesn't scale to high dimensional problems, as you may be, okay. So this is really the problem, okay. So relating energy-based modeling, people have tried to just a good result of research is just how to deal with the Jacobian to make it more efficient, okay, and try to fit energy-based models with Fisher divergences, okay, to avoid the problem of long waiting times in Markov chain Monte Carlo, okay, with maximum likelihood we saw before, okay. So now we're gonna see what people two results, okay, to deal with the quadratic cost of the full Jacobian. Okay, one is the noise in score matching. Okay, and I think it's good to introduce it now because this is gonna appear again for diffusion models again because the idea is quite similar. So it's I think it was nice to just show this here. Okay, so Vincent Watt did like 10 years ago some way to just avoiding computing the second derivatives. Okay, and which is the idea is just, I mean, it's also quite simple. It's just changing the data distribution. Okay, so instead of working with our clean samples, we just add random perturbations. Okay, so we are gonna work with noise data. Okay, and of course, the noise distribution is well known. Okay, so we know the distribution, so the calculation simplify because we know the perturbation model. Okay, so this makes things very simple. Okay, and we avoid computing the full Jacobian, as we'll see in a few moments. Okay, so you might be wondering if this data corruption process is acceptable. The thing is, it depends on your domain. So in Kevin Murphy's book, he argues that if your data is like image data, you have pixels. Since pixels are discrete, right? You know, they are numbers from 0 to 255. It's okay to corrupt the data because you can just add a subtle perturbation that is smaller than the minimal pixel difference. So it's in that case, it's okay, right? Because you are not meaningfully change the distribution, okay? Because the perturbation is too small, okay? But the problem of this approximation if your clean data, if your original data is already continuous, you may not know which is the best amount of noise, you know, because you may be unsure of if the noise is small enough or you are really changing the distribution. So if you're working with image data, because it's discrete, the pixels are discrete, this is like feasible. But if you're working with continuous data already, adding another source of perturbation, this can be problematic because you are changing the distribution. Okay, so this is the argument they give in the book. Okay, so but why the people do that? Okay, because now since now we have this conditional. Okay, this is the noise function, which since this is a Gaussian, the gradient is just subtracting the mean and dividing by the standard deviation. So it has a very easy expression. Okay, so we can plug this back in the Fisher divergency objective, and it simplifies, okay, to this very, very handy expression, which is just, okay, the scar function, okay, over my corrupted data. And then this term, which they argue that this term really just, it's like trying to predict how, given my noisy data, how can I clean the data? Okay, so this is really the difference. Okay, so now, as you can see, now the Fisher divergence has simplified because we don't have full Jacobians. So this is quite efficient to compute. Okay, so this is a good way of doing things, especially for image data. Okay, it's okay. The problem is that, okay, this is what I was telling before, that we are learning really the score of the noisy distribution, not the actual distribution. So in some domains, this might be acceptable, but in some other domains, we are maybe fucking up the distribution, just to say it clearly. Okay. So, and this is really like the final trick, okay, for computing Fisher divergences is an alternative approach that they also talk in the Kevin Murphy's book. But I think it's a nice approach because I have seen in some other domains this same idea. Okay, this idea is what is called like the slicing technique. Okay, which is instead of just working with the divergence of two high dimensional, as you can see, gradients, we just take random projections. Okay, so by a random projection, this is just a scalar number, another scalar number, but we repeat this for a lot of random samples of random projections. Okay, so instead of just fitting two high dimensional gradients, we are just fitting projections, but repeating this a lot of times. So it's like simplifying the problem from a high dimensional problem to several one dimensional problems. Okay, so this is really the slicing technique, which is just introducing random directions to project the high dimensional gradients. Okay, and then doing the same thing, which is like the mean square norm. Okay, so if this is zero, the two distributions are the same, and the model has converged to the data. Okay, so and I think this trick can be useful because I have not only seen this for energy-based models. This slicing thing can also works for if you have working optimal transport like Wasserstein divergences. You can use. I have seen this trick in another paper just to reduce a high dimensional problem to a low dimensional one. So it has. I think it was interesting this trick. Okay. The thing is, this is the just the Fisher divergence expression, or if you want to call it the slice Fisher divergence. Okay, so we can use the same integration by parts in the Havrilen original paper, and now the expression simplifies, okay, to these two parts. Okay, notice that now we have the score function, okay, and we have a Jacobian, but the Jacobian is not alone. The Jacobian is really multiplied by a random direction, okay, and the thing is, well, if you have worked with automatic differentiation, okay, you know this result, but computing this is much feasible because it's a linear cost instead of the quadratic cost. Okay, so this is a non-result, is automatic differentiation. Okay, so with score matching, okay, we have seen the different strategies. Okay, so the original one is consistent because we are approximating the original data distribution, but it has a very, very problematic cost. Okay, the denoising is also very more feasible in terms of cost, but we have to take care because we might be approximating a noisy target. Okay, and the slice it seems like a good compromise. Okay, because it really just doing some perturbation, but it's keeping the original distributions the same because we are not using a surrogate proxy to say so. Okay, so yeah, this is I mean, really, and this is some connection, deep connection that appears in the book. But there is some involved arguments. Okay, I not wanna take a lot of time here. That they are really score matching, and contrastive divergences or maximum likelihood, they are like the two faces of the same coin. Okay, because it can be shown that the Fisher divergence is related to the derivative of the KL divergence of some smooth version of the. So there is a connection between them. Okay, which is also a good result. Okay, but yeah, this is quite involved, and this is just really for a curiosity, but this doesn't give us information on how to compute things because the methods are what we are been showing. Okay, so just a connection. Okay, so and I want to focus on a third training technique. Okay, which is adversarial training. Okay, because I think it might be interesting for some of you that have worked on adversarial things. Okay, so really in the Kevin Murphy's book, they don't give that much time to adversarial thing. So I wanted to just change the order here and now focus on this part. Okay, so the thing is, if we go back to maximum likelihood, remember we need to get samples. So this takes a long time to converge because we need to do this at the beginning of the step. Okay. So the idea of adversarially training energy-based models, okay, is to use to introduce some kind of variational approximation. So this is really like some kind of variational inference, but not really because you're gonna see the loss is different. Okay, so we're gonna introduce an auxiliary model that approximates our energy-based models. Okay, so that this auxiliary model really just is gonna replace the sampling. It's like we are gonna try to amortize the sampling process. So one sample from the auxiliary model is good enough for computing the gradients here. Okay, so this is really like doing variational approximation. Okay, but there is a trade-off. There are trade-offs now that are gonna appear. Okay, because this is not the. Okay, there are some problems here. Okay, that we will see. Okay, so to do this, okay, how can we introduce? Well, we start again with the expected likelihood from the first part of the talk. Okay, we have this expression, and then we just the usual trick, which is multiply and divide by the variational approximation. Okay, and then of course, typical use the Jensen inequality to put the log inside the integral. Okay, so now after this change, okay, what we recover in the right hand is just the expectation. This is like really similar to the elbow in variational inference. We get the expectation of the energy function, but with a sample from our variational approximation. Okay, and we have some entropy here, then which is the entropy of the surrogate model, the entropy of the variational approximation. Okay, so we have really with this we have really created an upper bound, okay, in which we have here the two contrasting terms from before. One is from the data distribution, and the other now not from a Markov chain Monte Carlo, but rather a variational approximation. But we have this extra term here about the entropy of the sampler that we need to deal with. Okay, so yeah, of course, this is really like we're gonna optimize the bounds. But notice we have now two families of parameters. We have the original parameters from our energy-based models and the parameters of our variational approximation that we need to also optimize. So this leads to really a minimax problem. That's why this is called adversarial, but well, this is not really in the adversarial sense. Some of you might be wondering, but this is what people is calling that. Okay, so we need to, for one hand, minimize the upper bound, which is the variational approximation, and then of course maximizing the parameters because those are the energy-based models. Okay, because in the outer loop we are doing maximum likelihood. Okay, so this is really the problem. Okay, so as you may be wondering, this is really related to generative adversarial networks. It's like a similar problem with GANs, which is like this kind of minimax game. Okay, so of course here the variational approximation is like the generator. Okay, but the benefit here is that we get an explicit energy model, okay, because it's a proper density, not in a, which is not like in GANs, okay. But the thing is, we have also problems here because This is not free, okay, because our variational approximation, we need to deal with the entropy term, okay? So this makes the benefit we have at the beginning, in which I was telling you that the energy-based models can be any function. Okay, now we are losing because if we need to compute the entropy, it cannot be any function. So that's the problem with this. Okay, we need to do some kind of approximation. Okay, so now to the requirement for our variational approximation to replace Markov chain Monte Carlo is that it has to be fast because we want to replace the Langevin dynamics from before, and we need to be able to compute the entropy, okay, for the maximum problem as before. Okay, so that's why, well, I mean, of course, we can use normalizing flows like Roy explained it 2 weeks ago. Okay, but the thing is, we now are imposing a constraint, which is the thing we wanted to avoid at the beginning with energy-based models. So this might be like, why are you doing this? So this is, but this is people have done like quite recently. So in this paper from 5 years ago, from 6 years ago. Okay. But the other idea is just to use to go like the full GAN approach, okay, which is like, okay, I first generate some random noise from a known distribution, and then just I have a deterministic mapping that converts my noise to my sample data. Okay, so this is really like a GAN generator. Now this is unrestricted because it's just any deterministic function. But the problem is that, of course, we cannot compute the entropy. But so people have been working, and this is like more relatively recent research in how to approximate this entropy. Okay, which is approximating with an empirical measure or whatever. But you get the idea. It's just doing more approximations over the already approximated upper bound. Okay. So one of the recent ideas related to this is to make the entropy. Is read this recent paper by Grathol. Okay, we will turn to that later. It's quite interesting because it's to complement the generator with a perturbation in the outside. Okay, so we have this really conditional Gaussian distribution, which is like smoothing the deterministic generator. Okay, that's why it's called noisy neural samples. Okay, so now the thing is, since we have doing this smoothing process, we can now have a way of getting samples from the entropy. Okay, so we can just do the maximum problem easily before. Okay, so this is like the state of the art in adversarially training energy-based models. Okay, so this is like one of the most robust implementations if you want to combine adversarial training with energy-based models. All right. So, but of course, this has also this works well in theory, but in practice, of course, we still have the same problems we have with GANs, which is since we have a minimax objective, we have a lot of instability problems with during learning. So there is a lot of tricks also there. But this is like the state of the things, okay? So yeah, this is really like the full adversarial training pipeline, okay? So we get a random noise, okay? We use our sampler, which is replacing the original Markov, the original Langevin dynamics. So this is a sample from the model approximated. We get a sample from the data, and we estimate the energies, like minimizing the energy over the data and maximizing the energy over the model generated data, which is the original log likelihood for energy-based models. Okay. So let's but yeah, the thing is, people are like quite focused on training methods for energy-based models. So if you see the Kevin Murphy's book, they give a lot of like 3 pages devoted to noise contrastive estimation. That it's also another interesting, but I think it was more interesting the adversarial approach for some of you. Okay, there are a lot of tricks. Okay, but there has also been some success in training EVMs, but using alternative divergency measures like the strain discrepancy. Okay, this is like a different divergence. Okay, but notice we have a maximum here. So this is really like a minimax problem at the end, another minimax problem. So it's kinda tricky, because we have the same problems of saddle points and that stuff. Okay, but yeah, as you can see, let's not so far ago, this was a quite productive area of research because it's just people developing methods to avoid computing the partition function for these models. Okay. So now, just to wrap up this last 10 minutes or so, I just want to show you, because the book, this is just really the chapter of the book. I just want to show you two recent, well, from like 6 years ago papers for EVMs, just quickly. Okay. So the first one is like how people used to scale these to large scale problems. Okay, so this was a paper by my Mordak. He was an OpenAI. So they even OpenAI released the code. You can see in the GitHub from OpenAI, they have a code for this, which is from the era before OpenAI released things, open source, not now. Okay, so they applied, these two researchers try to apply all the tricks we have seen to make energy-based models scale to, in this case, real images. Okay, so they just use, but the thing is, I think this is like a bitter lesson because we may have fancy methods like adversarial training, but what they just use maximum likelihood with the language dynamics, the thing we saw at the beginning, and three engineering tricks, nothing more, because this is what really scales. Okay, so they have a replay buffer. Okay, which is in this chain that we have memory. Remember, okay, we just to avoid losing diversity, sometimes some with some random frequency we just reintroduce a previous sample. Okay, so improving diversity and mixing, just like in reinforcement learning, as I said before. Okay, they do some kind of regularization in the energy function, but this is to make the gradients more stable. Okay, and they also do some kind of regularization, which is new. So this is really the gradients from before of the energies from the data energies and the sample energies. And this is an extra regularization term that they saw it help learning better. Okay, but this is the idea. Okay, what we did, and really the thing is that this was like, I mean, for that period, like kind of the state of the art in, at least in this problem of image generation. Okay, the thing is nowadays these images look like shit. They are not the state of the art anymore, as you know, because of all the advancements in diffusion models from the following years. Okay, but in 2019 this was like quite the state of the art. Okay, because they compare the inception score, the Frechet inception distance, and it was quite competitive with the state of the art there, which were gains, generative adversarial network, of course, and also like autoregressive models from that era. Okay, which is quite nice because they saw that it can scale. Okay, also, yeah, they have a lot of useful properties when you train as CVMs, but I will explain this better with the follow with the next paper, which is for some reason, if you train and model like an EVM, you get adversarial robustness and auto distribution and better calibration than just using the standard cross entropy, at least for classification. Okay, which is the, I'm gonna just show this better with the next paper, which I think is clear there. Okay, so I think this is also I think this is also a very quite a revealing paper from 2020, which is that the title is quite funny because they state that every classifier is behind the hood an energy-based model. You don't need to change architecture or nothing. This is just a reinterpretation. Okay. So suppose we have, of course, this any classifier with is logits base and use a softmax. Okay, so that is like the mild constraint, the mild assumptions we need to use. Okay, but the thing is, of course, we get the logits, and as you know, we get the softmax to get the classification. Okay, but they argue in the paper that we should just take the logits like in a tensor way and just reinterpret them for expressing different probabilities of the model. Okay, so we can just express the joint of the model, not just the conditional, by taking the models and the exponential and then of course normalize, but also the marginal, which is just summing up in the along the classes. Okay, so if you do this, you really they really get, but this is really in a formal way. You don't need to change architecture. That any classifier based on logits, okay, they really expose an energy function, which is defined here, which is just okay, I take the logits and I just sum of them of in the exponential space. Okay, so this can be interpreted without any changes to the network as an energy function. Okay, so this is and they argue, of course, that since we can have this interpretation, okay, that we have any energy function inside, we should train classifiers to take into account the energy function using any of the methods we said before. That is going to have, and they show that if we, under this interpretation, and if we train this term, and not only the logits via the cross entropy for classification, we get a lot of benefits in our classifiers. Okay, because it's like bridging the gaps between discriminative models and generative models. It's like a way of unifying, which is why this paper was kind of good because it's the idea is like really really simple. It's just a reinterpretation, but it's nice because it's like bridging the gap between classifiers and generative models. Okay, so they call this method the joint energy-based model, but this really this can apply to any discriminative model, any neural network. Okay, so they argue that when training, okay, of course, we factor the log likelihood, which we can get from the logits using those arrangements from before. Okay, so if we factor this, we get, of course, the usual cross entropy for classification, which is the thing we usually do for training a classifier. But now we have this new term. Okay, this new term appears before because of this interpretation. Okay, so they argue that we, when training, we not only should be training the classification, but we should also train this part. Okay, and of course, to train this part, we need to use any of the previous methods we have shown. Okay, like long gaming dynamics or the persistent contrast divergence or adversarially training this. Okay, in fact, the adversarially training from before was a follow-up of the authors for this paper. Okay, in this paper, they just use long gaming dynamics. Okay, using the same tricks as the large scale study before. Okay, and then just apply to a typical ResNet without any changes. So they train it that way, and they find it's quite nice because they get an accuracy which is slightly lower than the accuracy for just a discriminator only trained same network. Okay, but you also get capabilities that you can also generate samples from these networks. And these samples, okay, they are not really as good, but they are quite competitive with an especially generative model only. Okay, the thing is with this interpretation, if we train with these two terms, we get a single model that can do discriminative and generative tasks at the same time, which is quite nice. Okay, this is what they show in the paper. Okay, but if you go to the paper, okay, you can see that really they don't just stop there. Okay, for some reason, which is can be surprising, they don't have a formal argument. This method also improves calibration. Okay, I think I'm just gonna show you the paper before because I have it over there. It's cleaning the paper. So this is really the paper. I hope you can see both of the tasks. Okay, so yeah, this is really the paper. Okay, let me just scroll down a little bit. Yeah, this is what we discussed. Yeah, these are just the comparisons for both the generative tasks, but they get that this is the calibration result, which is also interesting because if you just train a model with cross entropy, you know that you don't get calibration results. You need to use, if you want calibrated results, you need to use a post hoc method like the Platt scaling or whatever. But using this training, the model is good enough calibrated for some reason. Okay, so this is good. And they also show that these models can be straight out the way used for auto distribution detection, which is something that is not feasible with just a standalone classifier. Okay, this is also something you get for extra. And you get also adversarial robustness, okay, to adversarial examples, which is also quite nice. Okay, so maybe for those of you that don't know what adversarial example is, just we have a natural image and we introduce some noise. This noise is not random, it's just strategically optimized to put the classifier. So you can see the perturbation can be lower or higher. Okay, and this is the typical graphs of robustness. So the horizontal axis is the degree of the perturbation. Okay, and then in the vertical axis, we have the accuracy of the classifier. Okay, so with a base model, which is just a standard neural network trained with cross entropy, we get that if we start adding noise, the accuracy decays because these adversarial examples can fool the classifier. But if we train not only the discriminative part, we also train like an energy-based model. Okay, well, just with Langevin, there is no really adversarial training here. We also get some decent adversarial robustness, which is quite nice because if you think about that, they in the problem they don't impose any kind of adversarial in structures. It is like some kind of thing you get they are getting for free. Of course, it's not perfect, but it's comparable to a specialized method from which is like the state of the art back then, which is just explicit adversarial training. So this is something that I found it was quite nice, okay, for this method, okay, because you get a lot of things for, I mean, it's not free, but without changing the architecture, okay. So this is a quite nice result, okay. So of course, these things can scale. Okay, I just go back to the presentation. Let me just put this file screen a little bit. Okay, so the thing is, people saw that a few years ago, 2020s, that these methods scale, but then something happened because really nowadays, oh sorry, I did what did it change? Well, it doesn't really need this slide. Okay, what is really happening now, as you might be think about that, is that people don't, I don't know why, well, I have some thoughts about that, but people don't really work in energy-based models now. I think because what happened in 2021 and 2022 that we will see next week is that diffusion models appear, and at least for image generation and some other tasks, they are now, as you know, the state of the art. Okay, so this is really like the first paper we saw was a large scale of the 6 years ago. But nowadays, like energy-based models for some tasks got superseded by what was the name of this diffusion-based models, which is something we saw in the we are gonna see next week with Alberto's talk. Okay, I don't know why. I suppose that diffusion models are more sample efficient. They don't have you don't have to do a lot of tricks like we have to show you now. Okay, so maybe they scale better, and I don't know, maybe there is a cultural reason because people just prefer diffusion models because they may be seen fancier. I don't know, but this is like the state of the things. Okay, so people try hard to scale things in the 2020s. There are a lot of results, especially if you follow William Gathol. That this is the last paper, a good researcher from Toronto with the Dubenauts group. Okay, he has worked in energy-based models recently, but now the focus seems to be on autoregressive models, LLMs, and diffusion models. So I think this is like what has happened with these methods. Okay, so the thing is, these methods are just to summarize what we discussed. Okay, these are quite we can define them quite nicely because it can be any function. Okay, we can combine several functions together to impose structure. Okay, this is something we can see in the first paper. Okay, so I'm gonna show you this. Okay, let me check the other paper, which is the large scale. Okay, to justify energy-based models for image generation, but this is really at the end of the paper. Okay, this is the compositional generation. We talk about the product of experts. If you go to this is really in the appendix, you can see the experiment they do. Okay, what was it? Which is they train two independently EVMs and then they combine attributes using the product of experts approach. So you can see that this composes nicely. Of course, the quality is not the best, but this is really in 2019. But you get the idea that this is really the argument of compositionality, at least in the image generation domain. Okay, so let's go back to the slides. Well, I think we are almost finished. Where is the where is the slide here? Okay, and yeah, I think they have bits, as you can see. There is a lot of research, especially between 2010 and 2020s, of how to fit them because it's an interesting problem. You can apply a lot of tricks. Okay, they scale in the 2019s and 20s, but yeah, nowadays they are just superseded by diffusion-based models. So this is really the state of things for this part. Okay. So I think this was all I wanted to show you. So yeah, thank you for your attention. Sorry, it was slightly longer than an hour. Okay, yes, thank you for inviting me. And if you happy, I will happy to answer any questions or chat with you just now. Okay, but just before questions, just to reminder that next week, I suppose, is the next chapter, which is diffusion models. Okay, we introduce some concepts related, but we'll see that now something that is now most adopted by the community. At least is more trendy. Blah, blah. Okay, so this is all on my part. Thank you again.
Thank you so much, Victor. Are there any questions?
Well,
Well, if not, I can. I have a few. I can get started. Uh, I mean, the most striking result for me is the adversarial robustness you get for free, basically. Do you think that is a result of the energy-based models themselves or a result of modeling in a generative way, so modeling the data distribution itself? Because then, I mean, like, for example, that kind of reminds me of these purification methods where you're using the data distribution to kind of undo the attacks. Do you think that is the reason, or it is a result of the architecture or the way the modeling is done itself?
good question, Pablo. I think it's really a result of you are better modeling the data distributions, so you are leaving less gaps in the
Hmm.
distribution. So the space to say is like more covered and more smooth. And that is not this is not really for the architecture, it's really because of this is really like a regularization, but it's a regularization well done in the sense that you are better modeling the frontiers of the space, so you are less prone for adversarial spices because you are leaving out less holes to fill
Hmm.
adversarial examples. So this is like, I think, yeah, you are better modeling the frontier between classes, or if you want to see around, but because this generalizes between architectures. So I think this is really an effect of the regularization. Okay, they do that.
Thanks. Yeah, that was a bit my intuition as well. There's a question by Max in the chat. I don't know if you can read it. If not, I
Oh,
will.
yeah, I think I can open it here. So Max asks, is there a sense in which the ellipticness of the energy in theta is necessary to make the replay buffers effective? Let's say, well, I don't, I don't really know. Okay, because that's a good question, but yeah, I'm not really sure about that. So sorry, Max, but I think, yeah, if you wanna, I think it may be related because if you wanna keep the replay buffer effective, maybe your sample is from a long time ago, so you don't want your energy function to change that much. So that's why they impose the ellipsisness to the energy function, so they don't change drastically. So the previous sample from a long time ago, it's still valid in some way. So I think it may be related to that. Okay, to not make abrupt changes in the loss landscape. Okay, but I don't think, or I don't know if in the paper, the other paper, if the authors have made the ablation study, because they should have made an ablation comparing the replay buffer with or without lipsys. I don't think they have done. Well, maybe they have done in preliminary experiments, but at least in the paper, I didn't found that. So we can only guess. Okay. Thank you.
Are there any other questions?
I do have one. Thanks for the talk, Victor. Um, do you think that that property that EVMs have of closing the gap between classification or discriminative models and generative models.
Mhm.
Even though now they've been overseeded by diffusion models, do you think that maybe in the future we find out that they're more useful than we thought just because of that property, perhaps?
Yeah, yeah, definitely. In fact, there is this paper in which they show the joint tendency based model. It has a lot of it has like almost 1,000 citations from more recent papers. So people are just improving, training jointly the generative and discriminative part, but using the tricks for the generative part, and it shows it you can get even better benefits. Okay, so yeah, you can definitely improve on the part by using the tricks to train the energy based model part, if you're gonna say. There are a lot of applications also in robotic trajectory manipulation and that stuff. But what I think is happening is that really at the end researcher time is limited by human people. I think people are just focusing on diffusion models like a cultural thing or language models instead of just revisiting these ideas, which maybe could be a nice avenue for for an interesting paper. You get it? Yeah, so it's
Hmm.
like some kind of, yeah, I think people in research and they follow trends. So nowadays there is not a trend for a based model. That was,
Hmm.
the trend is other thing. So I think that is happening. But yeah, definitely if you see this paper, it has like almost 1,000 citations, and there is some interesting follow-up work expanding that. So
Hmm.
treating the models as combining them, but then trying to make it better the training process. And that's it. So yeah, people are working on that, but not as that much as some other topics like diffusion models and that stuff. Okay.
Okay.
Well, if there are no other questions, I think we can conclude this session. Thank you so much again, Victor. It's been really interesting.
Thank you,
Uh,
June.
yeah, that's it. We'll see you next week because we moved the schedule because of the Easter break. And we'll see you next week with diffusion models. Thank you so much.
Perfect. Thank
Thank you,
you too.
Victor.
Bye bye. Thank you.